In this case study, I'm going to spend some time talking about the Brumadinho disaster and take a close look at the INSAR data available leading up to the event. This is an excerpt from a Slope Stability 2020 paper by a colleague of mine looking at actionable displacement prior to failure. I'm sure we're all familiar with the situation. The dam failure released millions of tons of material with a catastrophic loss of life. There are several questions one can ask of the SAR data. For instance, was there displacement at the failure site right before the failure? And that is certainly an interesting question to ask. But it's in danger of becoming a self-fulfilling prophecy, focusing on one area, tuning a processing chain to get the best possible results for that area at that time, at the expense of other considerations. This is not a realistic situation in a monitoring campaign, because it's like looking at security camera footage after you know what happened. So a different question is, what would a normal monitoring campaign have discovered? Not just on the dam face, but in general, using a more typical generalized processing chain. What is the data like in that region using that approach? Are there any discoveries on the dam face that are statistically significant when compared to other areas? The site in general is tough for standard INSAR, with mostly low coherence, including in the area of interest, possibly due to vegetation effects on the dam face, but also soil moisture could be a factor too. The bottom figure here shows the SAR data that was available. On top you can see the Cosmos SkyMed dataset. This is an Italian X-band satellite that has a reasonable stack of descending images. An orbit direction here is important, as we shall see. Sentinel-1 has two excellent stacks of data going back years, but low resolution of course. These are also both descending. And then at the bottom there is a good stack of TerraSAR X images of ascending images. So this was the approach. Try and be consistent, avoid fishing expeditions either spatially or in time. Use metrics for statistical significance rather than just eyeballing it. We're first going to look at the short-term interferograms just before failure, which relates to the question, what would rapid reports or rapid bulletins have reported? These reports are frequent, delivered quickly, and designed to highlight new and ongoing risks. Then we'll look at longer-term time series analyses. These take maybe 15 or more images, and they have lower noise and show the evolution of displacement over time. We can ask whether there was any long-term displacement and whether accelerations are evident prior to failure. So here's the first of 4 slides showing short-term interferograms prior to failure. Would we have marked anything in a rapid style report? This is the first of the 2 Sentinel descending stacks. Let's call it track 053. And this is a 12-day interferogram, 3 days before failure. To be clear, the Sentinel images from different tracks have a large overlap, so it's quite common to be able to see different areas from more than one orbit track, even if it's in the same direction. On the right, you can see the satellite's heading and the look direction. The dam is sloping away from the satellite, which is what we want. So there should be reasonable sensitivity to downslope displacement. Resolution, though, is only 20 meters. So in a way, it's kind of the right direction, but it's the wrong resolution. The black polygon shows the dam face, and on the dam wall, there are some color changes, but they are consistent with noise elsewhere in the data. If you decide that they are significant, then many other hundreds of such areas elsewhere in the rapid report would also warrant equal consideration, and the rapid report would become useless. At the back of the pond itself, just right and up from the black polygon, is a yellow and purple area, and that would catch the trained eye. It's different to the other features. It has structure, and it progresses from blue to pink to yellow in the center. So it could be displacement, but it's an area in which we expect displacement and don't necessarily care too much about. Here's the other Sentinel pass. Let's call it track 155. This is also a 12-day interferogram, 8 days from failure. Again, it's descending, and again we have the right direction but really the wrong resolution. And also again, nothing of significance on the dam face that we would highlight as anomalous displacement. Up and right, the purple and yellow area is, as before, present. So now 2 independent data sets show the same feature, which is somewhat encouraging when you have noisy data like this. This is the TerraSAR-X data. And the improvement going from Sentinel's 20-meter resolution to 3-meter resolution is striking. But it doesn't do as much good because the ascending pass looks directly at the dam wall. This causes 2 issues. Firstly, the slope will be foreshortened. Remember that when the ranges to areas are similar, the echoes return closer together and the area is compressed in the raw data. This effectively translates to lower resolution, just where we need it. More seriously though, the sensitivity to downslope displacement will be poor from this direction. We want slopes to face away from the sensor because the closer the look direction and the direction of displacement align, the more displacement we can capture. If the displacement is really small, then we really need that extra sensitivity. So a TSX descending pass would have given us the chance of capturing this displacement if it's present. Note that again we see the purple and yellow displacement area behind the dam wall in the pond, but nothing on the dam face. And this is the Cosmo SkyMed data. This is also X-band data, just like TerraSAR-X. The resolution is also 3 meters, just like TerraSAR-X, and it's acquired from a descending pass, which is what we need. Unfortunately, though, the data is just not as good as TerraSAR-X. This is often true of Cosmo data, but this is a particularly striking example. The main feature within the black polygon is a yellow, purple, blue ramp, which is likely a remnant atmospheric effect. Removing atmosphere when you have small, coherent areas surrounded by noise is particularly challenging. So even considering, though, this atmospheric bias, there are no small telltale displacement-like signals on the dam wall. It's also normal to wonder what longer-term interferograms might look like. Notice the reduction in coverage, though, after only 33 days. And then after 55 days, it's almost completely gone. It's not completely clear why coherence would reduce so quickly on the open dam face, although we do know that there is some minor vegetation on the surface, but it's hard to tell what that's like from optical imagery. Moisture content in the soil could also be a factor here. These are the kinds of interferograms that we need for detecting subtle displacement. As the duration of the interferogram increases, this usually means there'll be more displacement that has occurred, and there's a higher chance or a higher signal to noise. We need that displacement signal to rise above the background noise, but that only works if there is coherence in the area. In Arizona, for instance, if we were looking for subtle displacement, we're at liberty to form and analyze interferograms that are a year or more longer. This might reveal displacement due to dewatering, for instance. But on this site, something destroys the coherence after only 33 days. The next obvious thing to try is to amalgamate any coherent short-term interferograms and mathematically solve for a displacement rate using a multi-temporal approach. So here we're leveraging the spatio-temporal statistics of each dataset in turn to come up with these 4 results. Here the heat map is scaled to plus or minus 30 centimeters a year. We see excellent agreement between the datasets for the displacement in the pond itself, but we really need to scale it much more aggressively if we want to see that subtle displacement. So here is the same result as the previous slide, but this time scaled at plus or minus 5 centimeters per year. The color map we're using now saturates completely at dark red at minus 5 centimeters, which should also reveal lower magnitude displacement. But zooming in like this also means we blow up the noise, and this gives us an idea of which datasets are the noisiest, and we can see how much noisier the CSK, the Cosmos SkyMed data is compared to the other 3. The Sentinel 053 track shows lower noise as well as what looks like displacement signal on the lower portion of the dam. This had some research groups quite excited. But when tested using signal to noise ratio metrics, we find that this signal is not statistically meaningful, and we're forced to conclude that this area wouldn't have been marked as displacement in either a rapid report or a longer term analysis. Another way to look at the data is to view the signal to noise ratios for each pixel in each of the 4 datasets. So here we have a map of our signal to noise estimates scaled at plus or minus 5 standard deviations. So the darkest purple here is 5 sigma or more, and a 5 sigma confidence level represents around a 1 in 3.5 million probability that the results could be obtained by chance alone, or the 99.9999 confidence level. For comparison, 2 sigma is equivalent to the 95% confidence level, which sounds great until you realize it actually only represents a 1 in 20 probability that results could be obtained by chance alone. Of the many millions of pixels in an INSAR analysis, there will be plenty of 2 sigma areas that are not real, especially with noisy sites like this. So in summary, in all 4 datasets, we don't see any areas on the dam face where the displacement signal is significantly above the noise floor and highlighted by one of these white contours. Finally, let's look at some time series and see if we can see any likely accelerations. So here we have 1 graph per sensor, per data set, I should say, and each of these graphs plots all the available data points within area A, which is where the failure initiated. Please ignore areas B and C. The red line in each graph represents the average velocity for the points in area A. The first thing to note is the amount of variance between the points, which is a telltale sign that noise is higher than we would like. Next, note that there is displacement at area A, but it goes back years. Focusing on the right-hand end of the graphs, though, there is no obvious sign of acceleration prior to failure. Sentinel 1053 has a small downturn prior to failure, and others have pointed to this kink, but when you measure it statistically, it's not really anomalous. There are other similar kinks in 053's own time series and also in other data sets. So it seems unlikely that this would have raised an alarm. And consider other areas. Many of them show displacement and kinks like this. So if you decide that this is worthy of attention, then thousands of other areas might be too. There's also something of a seasonal trend in both Sentinel-1 results. Flatter displacement from May with more activity from September to April. And the kink on the right-hand end of 053 therefore could be explained in that context as seasonal displacement. So in conclusion then, there is nothing anomalous about the displacement leading up to the event from INSAR, just steady state creep with some seasonality. This conclusion admittedly went against the grain somewhat, with other papers declaring that they could detect displacement at the failure site. But as I say, they were mostly asking a different question to us. Our question related to what would have been reported as part of a monitoring campaign. When the expert panel released its finding, though, we felt somewhat vindicated, and this was one of their conclusions. They found no signs of distress or large deformations in the data, and also the smaller deformations were not considered a precursor to failure, but consistent with ongoing creep. In summary then, the data quality is not great. This is basically the polar opposite of the CADIA case study. So INSAR is not a catch-all technology that can detect any failure precursor signal. There was nothing reportable that was statistically more significant than many other areas, either in short-term rapid reports or in deeper time series analyses. Only the shorter term interferograms had any value. Ideally, what we need here for subtle displacement is longer term interferograms, but still coherent interferograms. With more time, you usually get more displacement, so a better signal to noise. So the precursors to failure are either likely too subtle to detect or too sudden. If they're too sudden, they occurred on a timescale shorter than the SAR image frequency. And the conclusion we came to was later corroborated by the expert panel.